Hello, friends. It's good to see you on this beautiful day. There. So now I have your attention. Welcome back. So I spent the morning looking at your quizzes from last week and looking up all of the songs. Thank you for playing along with me. Most of you did. Jihong, you owe me one still. Don't think I didn't notice. Such a range of creative choices. I really liked it. I had no idea that Right Said Fred was not a one-hit wonder. Who gave me that one? No one wants to admit it? No? No, there was another Right Said Fred song. I was really impressed that I hadn't heard it in a stadium already. It was just a great choice. Lots of classic rock, The Who, Neil Diamond. Gentleman in the back, not here yet. I can't salute him, but yes, I enjoyed that. Thank you very much. And I noticed that everybody turned in their first homework. Hooray! So, perfect record so far. I hope to have those back to you by Wednesday, and that way you'll have a chance to complete whatever revisions you might need, if there is any. I don't expect a whole lot, by the following Friday. So no homework, no quiz this week, a little bit of a reprieve. And just in case you didn't have enough to do without homeworks or quizzes, I found some new articles and I added them to your stack. So on the website, I have updated the printable version of the syllabus to include the new references. They are also in Blackboard in a separate zip folder that you can download. There's 4 new articles, and I added them to this unit. So they are all about CFA and fit indices. I picked them because I thought they did a really good job of conveying why it is the case that sometimes your fit indices do not agree, and giving you practical advice as to which ones you should believe under various circumstances. So these aren't simulation studies. They're actually reviews of simulation studies. The SHE one is a simulation study, but they also do a good review, and they give prescriptive advice as well. So I liked those, and I also, the CFA spreadsheet that goes with example 4, I tweaked that over the weekend as well to update one of the pages to do a better job with that page, because I had forgotten I had built something better than what I had built for a different project. So if you have already downloaded the CFA spreadsheet for example 4, please get it again. And the new spreadsheet, the updated page, goes with this article here. So let's see. You'll notice that I gave you a zip folder of M+ input and output files. We just had a question about that. Let me show you what. So they're all the outputs that go with example 4 labeled by model. The input is all in one file. And you don't have to have M+ to access these files. These are just text files. You can open them in Notepad, WordPad, Word, whatever you want. So the same thing will be true when you get your own output. You don't need to have M+ to refer back to it. You just need M+ to actually estimate the model. So new readings, things coming back. Any questions, concerns? No? We're good? All right. Well, then tell me what you remember about last time. As usual, I will take words, gestures, letters. What are we talking about now? Start there. CFA. CFA stands for Confirmatory Factor Analysis. So sometimes it's confirmatory factor models. You can use those terms interchangeably. What is CFA for? Confirming factor structures, testing dimensionality, how well the items predict, how well the factor predicts the items, for what kind of items? Continuous and normally distributed. So in other words, not items you're probably used to seeing on a scale. But it is by far and away the most common practice in terms of how to address dimensionality for those types of items, so we will start there. And also pay attention to situations in which that may or may not work based on the data that you have, not just the number of item responses. So CFA model. There are 3 item parameters. Do you remember what they are? I'm going to open up Word here and type along with you. This is my version of writing on the board. That way folks at home can play along. Let's go with big font. Yeah. Hang on one second. Yes, there is. 1 second here. Item parameters. Intercept, there's one. What's another one? Slope, otherwise known as loading, yes. Those terms are interchangeable. And one more. Error, yes. So in the equations it's E, but what is the parameter? Everybody's error separately, or looking for a word that starts with V? Variance, yes. So error variance. Synonyms for that: residual variance, unique variance. No matter how you spin it, it's error. It's everything that's not the factor. So if we were to define each of these things, what's my intercept? Not quite. Not quite. So the mean of the item across people only holds in certain cases of identification. More generally, it's a conditional mean. So if you go back to the definition of an intercept from regression model, expected y, which is the item response in this story, when x is 0, so factor is 0. So a factor is a person parameter. It's a person standing on the latent trait that is supposed to predict the item response. So this, when the factor equals 0 part, that's what differentiates this from being a mean versus a conditional mean. Because oftentimes, the mean of the trait is specified as 0, but it doesn't have to be. And the intercept is going to shift based on the definition of what 0 means with respect to the factor. So then the slope. Yep, increase in y per what? Yep, per unit change in x, which is the factor here. Yep. So we want our slopes and loadings to be positive and big. What's the worst slope/loading you can have? Yeah, 0. Even negative is informative. And you'll sometimes see that if you forget to reverse code things, that you'll have some things load negatively and some things load positively. I have seen convergence issues when you don't, for no other reason than that. So I generally expect all of the items to go in the same direction. Whether you make them all negative or all positive is up to you. Error variance. Leftover, yeah. All the reasons why somebody gave that answer that is not their factor score. Good. Two kinds of solutions. So you're going to get output of each of these things in what is known as an unstandardized solution. What is the unstandardized solution trying to reproduce? Yes, the original item response, and by that more specifically, I mean item means, item variances, and item covariances. And actually, if I reorder this, covariances and variances, each of those, we will see more about this today, applies directly to the parameters below. The intercepts are trying to capture the item means. The slopes and the loadings are trying to capture the covariances. And then the error variance is trying to fill in the gap between what is predicted by the slope and what actually is the original item total variance. There's a one-to-one mapping here. So the other version of what we'll get, standardized solution, in which we will say the factor variance is going to be 1, item variance is going to be 1. So what is a standardized solution trying to reproduce instead? Dang, item correlations. Yep. So each of these solutions is useful for a different purpose. What we will see later in the units when we're talking about measurement and variance, for instance, if you're trying to see how well your instrument works in certain groups versus another, if it works the same, we'll use the unstandardized solution to answer that question. Whereas within a single group, within a single model, if you're interested in whether one item is a better indicator of the trait than another, the standardized loadings are going to tell you that more directly because they are corrected for differences in the scale across variables. So we will get used to both of these types of solutions in our output. All right, I think that's sort of the big picture stuff. Pictures. Picture time. Boxes are real things. Circles are model estimated things, variances. Directed arrows are regressions. So this picture is saying that this factor, which is a latent variable, meaning we don't know what it is predicting the answer to y1, and so is the error for 1. So you put these back together again and you get what y1 is. So this much is true on the top here, this much is error. The loading here is labeling the path. Two-headed arrows, covariance between factors. So it's an undirected relationship. You're just saying they're related to each other. If you wanted to, you could turn that two-headed arrow into a single-headed arrow on either side. So if it's pointing into F2, you would be saying that F1 is the predictor and F2 is the outcome. Or you could flip it around, and you could say that F2 is the predictor and F1 is the outcome. Those are all equivalent models. They will fit exactly the same. So, yep, because all you have to work with in the data is a set of covariances. So there's no way to use the model to tell you which came first in the sense of which should be X or which should be Y. Stupid triangle thing down here. That's a column of ones by which people have found a way to put the means and the intercepts into the picture. So each item has an intercept, each factor has a mean, each factor has a variance, and if there's more than one factor, they have a covariance. So this is all the stuff that you're asking your program to find for you. And these terms are divided into two kinds. Measurement model, which is item things. So that's where we get our item intercepts, item loadings, residual variances. And structural model, which is factor things. Factor means factor variances, factor covariances. And this distinction will be important because you always want to make sure that your measurement model is in good shape before you start looking at your structural model as to how these factors to relate to each other. So there's a sequence by which people look at these things. And this is standardized solution, and this is where we left off. So, questions? Ready for new stuff then? Yeah, that wasn't rhetorical. Are you ready? Yeah? Sure. Great. So, more equations. Hooray! I do want you to get used to the way that CFA and SEM models, oh my goodness, I can't believe I just said that. I need more caffeine. Yeah, don't ever say SEM model, by the way. That's like ATM machine. It's SEM is model. So you're saying structural equation model. That's a dead giveaway that you don't know what you're talking about. So, yeah, I apologize. Apparently the coffee wore off. I didn't want to come in here manic like I usually am, so I didn't have my due. And that's the result, SEM model. I can't believe I said that. But yes, I want you used to being able to read people's descriptions of these, whether they are in scalar equations like this, where it's one item per equation, or matrices, or words, or whatever, because you're going to see it in all different forms. So that picture right here is expressed as this set of equations. So y, again, is the item response. Here's the 3 from the first factor, and here's the 3 from the second factor. Each y only has one possible intercept. So whether or not it's measuring one factor or two factors, each item gets one intercept because it has one mean in the original data set. And that's what these intercepts are for, is trying to reproduce that mean. So the loading of item 1 on factor 1 is shown here, and the non-loading of item 1 on factor 2 is shown explicitly here with the 0. And the opposite pattern shows up for items 4, 5, and 6. They don't load on factor 1, they do load on factor 2. So this is the big difference between confirmatory factor analysis and exploratory. In exploratory, there are no zeros. There are loadings everywhere. I told it, no, zeros for this one and loadings for that one. So that's the confirmatory part. You're setting up the structure that you expect. You ask your program to find the most likely estimates for all of these parameters, and then you see how well you did in reproducing the original data.
So this would be showing a two-factor model.
This is a two-factor model. So things that are not in those equations, there's no reference to the structural model parameters. Those equations don't tell you that f has a mean and has a variance, and that there's covariances between the two kinds of f's. But the matrices do include that information, at least the variances and covariances part. And also, note that what is here is E for each subject, but the estimated parameter is the E variance across subjects. So there's an asymmetry in that this is one loading. You get one number, but your output will never have one E. It will have the variance across people for each item. So each item in this has, each item parameter has a subscript that means that each item gets a separate version. Each item gets its own intercept. Each item gets its own residual variance. In special cases, you may want to change that as well. So for instance, if you are trying to do something like a growth model, in that case, you would start with a model where all of the intercepts are the same, which would be saying there's no change across items, and test it against something where they get to be different. Whether or not these loadings are the same, that's going to be the test of tau equivalence, or true score equivalence, equal discrimination. We'll get to that towards the end of this lecture. Likewise, whether or not these E variances can be the same is the test of parallel items. Yeah. So intercepts. So each, basically the idea that there's a 1 after everything here means that this item gets its own version. There's no sharing of parameters. The only thing that is shared across these equations is the f, because it's the same factor that's causing this person to answer all these questions the same way. So each person has one value on F1, one value on F2. So the loadings are the discriminations. They indicate how related the item response is to the factor that is supposedly causing it. The intercepts are the difficulties, and they're backwards. Higher intercept means a higher mean when the factor is 0, but that logically is easiness, not difficulty. When we get to IRT, that will go the right way again. And then each item gets its own error variance left over. So the constraints that I had mentioned, and this is coming later in the slides, just wanted to give you a sense that all of the assumptions of alpha are built into these models. So we end up with a test as to whether or not this needs to be 2 factors, or 1 factor, or even 3. And whether or not these 3 items could share one common loading and still do just as good of a job at reproducing the data, that's a testable hypothesis, and that's how you test tau equivalence or equal discrimination. Likewise, whether or not these items could also share a common error variance, that's a testable hypothesis, and that's how you test parallel items. Yeah?
So I know you explained why each
Because I didn't use any more interesting labels, I call these F1 and F2. So I could have went like FA and FB or something, right? But that's what that means. Yeah, that was probably not a good call on my part. No, I need to make a note to change that. But yeah, the S is because it's each one per subject, whereas there's no S's on the item parameters because they're shared across subjects. So it's one per item.
One value for each factor.
Yes.
Okay, but it differs by factor.
But it differs by factor, exactly. Yep, so if this was a unidimensional model and we didn't have F2, then you just have a set of loadings for F1 all the way down, and each person would have one score that is supposed to have generated their 6 responses. Now we're saying that there's 2 scores. Yep.
Is something like the error variance going to be the same across people? The error variance for a given item is the same across people. So why is S in this notation at all?
Because this is not error variance. This is the error for that. Yeah, it's like this is like the -3 or something because it's off, and that collection of offnesses is the residual variance across people.
What about for the factors, given that the factor won't change by people?
The factor does change by person. Each person gets a factor score. It's their version of the latent trait. It's their amount of anxiety or depression or social support or something else, right? Today I'm a psychologist. I'm sorry, all my examples are from psychology. But yes.
If you wanted to build a model where you had like 2 factors predicting one item, would you take the 0 out of the equation?
Yep. By the way, you're not writing equations in the software. You know what you're writing? I'll show you. Here's a preview. You are writing sentences. Sit, for instance, our factor is going to be forgiveness of situations, is measured by that item, that one, and that one. That's it. So if you wanted to have 2 factors, which, spoiler alert, we're going to have in this example. Let me find that. Here we are. I have a sit P factor that's measured by these 3 items, and I have a sit N that's measured by those 3. So if you don't list an item after this by statement, that is an implicit 0. If I decided that I want item 5 to be part of the second factor and the first factor, I throw it up there. And that's my choice. And so then I would get 2 loadings for item 5. But still 1 intercept and still 1 residual variance. Does that help? Okay, good. Go back to that. All right, other questions?
Does that program knows that you put it in both places at that point?
Yep. Yeah, it's super easy.
There's 6 variances, would it be 21 pieces?
It is, we haven't gotten to that yet, but it is 6 times 7 divided by 2 plus 6. So 21, I think that works out to be. 21 variances and covariances plus 6 more means, which is 27. There's an equation for it. But yeah, so the total data to be recreated from 6 items is going to be 6 means, 6 variances, and all possible covariances between the 6 items, which I think works out to be 15, if memory serves. You do this often enough, you just start to remember these things. They're like multiplication tables.
What was the last part? Variances and all possible?
All possible covariances among the 6 items. So if you picture like your matrix, all those off-diagonal elements, it works out to be 15. So there's 27 pieces of information available, and we are asking for fewer than 27 things to come back. So this is where we get into model identification, which is coming very soon. But right now I'm just trying to get you used to what's in the model and what do they mean. Other questions? Okay. So this, I think, is a more interpretable version of how this works. The program EQS, do any of you use that, seen that? That's what I started out in SEM. You literally write the syntax like these equations, so I tend to think that way because that was my first exposure to this topic. So then we get into the predictions here, and what is going to matter when it comes to predicting models, those 27 pieces of information. So the intercepts, so long as each item gets a separately estimated intercept, those 6 intercepts are going to perfectly reproduce those 6 item means. There's a one-to-one map. So unless you put some sort of constraint that says the intercept for each item doesn't get to be whatever it wants, item intercepts don't cause any problems. Likewise, if each item gets a separately estimated error variance, so I'm trying to denote this as variance of these E terms, then those residual variances will perfectly fill in the gap between what the model says and what the original item variance was supposed to be. And so there's no problem there, one-to-one again. Each residual variance is seeking to patch the hole between the model and the original item variance. So the item variances are going to be perfectly recovered as well. That leaves the one thing here, the factor loadings. There are going to be, in models that are testable, fewer factor loadings than are covariances. The job of the factor loadings is to capture those covariances. To the extent that they do a good enough job, your model fits and you have support for whatever structure you've said that it has. 1 factor, 2 factor, 3 factor, etc. So this is the thing that we pay attention to. How well do those loadings recreate the item covariances? So here are the equations by which the model recreates each thing. And I'm going to flip back and forth between my picture and that slide because I think it's easier to follow when you can point back to that. So I just made a copy of my picture for right now. So in SEM books, they sometimes refer to tracing rules to describe how the predicted relationships gets formed. So how does the model say that item 1 and item 2 should be related? Well, it takes this loading and that loading. And in this case, if the factor variance is 1, which it commonly is for identification, then it's just those 2. So 2 items from the same factor, their covariance is formed by the loading for the first item, the variance of the factor that they share, hey, stop that, and the loading of the next item. In the correlation version, the variance of the factor goes to 1, and these are the standardized loadings instead. So that's how they predict what the correlation should be between any 2 items.
But you know what the correlation is.
Mm-hmm.
Why do you need to predict what it should be if you know what it is?
Because that is how you say that you have the right factor structure. If all of these items are measuring the same thing, then that is the point of the factor. It is capturing the correlations and the covariances. That's what it's for. So the way we talk about the CFA equations is like we're trying to predict the item response, but that's not actually what we're trying to do. So this is very different in orientation than, even though it looks like a regression model, the point of doing this is very different. The point of doing this is not to understand why some people answer to 1 and some people answer to 2. It's to use those patterns to demonstrate evidence for the fact that those items are measuring the same thing. So those of you who've had me for multi-level, I talk about the model for the means and model for the variance, that terminology. Loadings are part of the model for the variance. Their job is to predict covariance. Their job is not to say why some people's Y1s is higher than other people's Y1s. The factor is the reason for that. So then when we go back to the picture, the idea of why is it that some people have a higher factor score than other people, that then gets into the explanatory part of it. And those F1 and F2 circles can be part of a system of equations at that level, at the structural level. They could become predictors and outcomes. So this requires thinking about data in a different way, because the object is not to explain the Y responses in the sense of how you typically think explain, right? What predictors, what covariates. We are simply trying to see whether or not the relationships among these items can be captured by this model or not. To what extent those relationships between the items can be captured. So items from different factors then. So if I had, say, 1 and, what did I do here? 6. You go from the loading of item 1. You have to cross the bridge here to get to the covariance between the two factors, and back down the loading of item 6. So this model says the only reason for the covariance between item 1 and the covariance, and item 1 and item 6 is because the factors are related, and that's it. So the same covariance should occur between any two items on different factors, just amplified or diminished by the size of these loadings. So that is down on this part here. And to get back to the original variance in any item, it's the variance of the factor times its loading squared, plus the variance of the residual. And that will perfectly recreate each item's original variance. So this is the truth part, true score, and this is the error part, unique part. Okay, how are we doing? Not exactly. It's just the first part of what you said.
But the point of doing the measurement model, do you know what I'm saying?
Mm-hmm.
What's
the end
goal?
goal? Yeah, so this is the preliminary work that would make sure that your items are measuring one thing or two things, and then you would then take those 1/2 things and go put them in a bigger model with other constructs in it and see how they're related.
Better than averaging the items, because
when you average an item, when you create a sum score, you're actually assuming parallel items in doing so. You're assuming dimensionality, and all items are equally good, and they all have equal error variances. That's the only situation in which there will be a perfect correlation between the factor score and the sum score.
So using items like in an average like that introduces error into whatever association you're actually interested in.
Yep. Measurement error.
Yeah.
Mm-hmm. Yep. The idea is that this latent variable, this F1 or this F2, is supposed to represent the construct of interest more cleanly than any one item would. It literally is like all of the covariance between those items in a circle, and you put a name on it. And whether or not you put the right name on it, that's a validity argument, and that is not my class. That's someone else's. So yeah, the point is to reproduce the item means, variances, and covariances. And really, it's the covariances that matter, because the means and variances will always be reproduced to the extent that each item gets its own intercept and its own residual variance. It's the loadings. It's all about the loadings. Other questions or things you want to hear again? All right, so these same ideas then. This slide of how those predictions get made by the model can be shown more completely through matrices. I am not a matrix person. I will never be someone who looks at something like this and says, of course. That's my husband. One of my favorite stories about him is he was looking through Craig Ender's book on missing data, which is on your reading list because I really like his description of maximum likelihood. And he's flipping through it, and he kept saying words, 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 until he finally hit some matrix equation. He's like, oh, good. I was just like, who does that? He does that. But no, but you're going to see that equation up top. Anytime someone says, I did SEM, it'll be in your more technical readings in this chapter, and so I want you to be used to seeing it and at least know what the stuff in it is. Once upon a time, you actually had to tell the software what models you wanted this way. You had to fill out matrices. That was the first version of Lizral that came about shortly after I was born, actually. And I heard a story from Susan Embridson that people who figured out how to use that package to fill in all of these matrices correctly in the early 80s, they called themselves Lizralites. It was like a tribe of people who had conquered this software, and they were very proud of themselves. And for a long time, it became sort of a rite of passage. Well, I had to do it this way, and you're going to learn to do it this way. And then Lizral itself was like, okay, no one's going to buy this anymore because this is just too hard. And so they now have actually a simpler language that you can use in addition to the old school matrix language. But yeah, this used to be how it was. But this hopefully will make it a little more concrete what the data are that are going in and what is being predicted by this model. So sigma here, this thing, this is the data. So the means for these items are not part of the story. I could have put them off to the side, but they're basically irrelevant in terms of predictions because so long as each item gets its own intercept, the means will be reproduced. So this is my 6 by 6 item covariance matrix. So it's square, meaning it's 6 by 6, it's symmetric. So for instance, this term right here, this sigma y2, y1, that's the same thing here as it is here. So on the diagonal is the total variance of each of my items. So item 1, hey, come back here. Item 2, I need to get a better pointer, hang on. Laser. Apologize to all you cats at home who are going to go crazy. Heather, didn't you tell me that your cat was watching this? You were like showing this on your TV and it was swatting at the mouse. That's pretty funny. So yes, you must have one of the smartest cats ever by now. Oh, okay. TV's bad for you? Even animals? Uh-oh. That explains a lot. So yes, item variance is on the diagonal here. So note it's sigma squared, meaning variance, whereas these are covariances. So it is how related, for instance, y1 and y2 are, y1 and y3, y1 and y4, and so on. So in terms of unique pieces of information, there are 6 variances, and if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 covariances. 21 pieces of information to be reproduced here. Because each item gets its own residual variance, this diagonal is going to be fine. It's the off diagonals that we're going to pay attention to. So what goes in to predicting each of these spots is explained by this equation right here. This is a lambda. I'm going to say maybe a phi or a phi. Want to take a vote? You don't care? Phi? Yeah, I wasn't ever in the Greeks, so I don't know most of the Greek letters. I know this one is psi because it's psi-chi. I was in that as an undergraduate. So this is lambda. This is lambda transpose, which means flipped over. That is how it gets the loading squared. So whenever you see something in matrices where it's a matrix, something in the middle, and then the same matrix transposed, that just means squared. For those of you who took multi-level, this is the exact same equation that gets you your V matrix, where the loadings are your Z for the values of your random effects. The middle one here is G, and the end one is R. It's exactly the same thing. Now, we have the loadings, the factor variances and covariances in blue here in the middle, the loadings on their side so that they get squared, plus the residual variances. So here are those pieces. The lambda matrix right here has either loadings or zeros. That's my choice. I choose which items load on which factors or not. So this idea that each item loads on only one factor, that's called simple structure. That's usually the best alternative because then there's a very clear relationship for what your factors mean on the end. So this is the same matrix on its side. Here is the variance of the first factor across people. This is the variance of the second factor across people. And this is the covariance between the two factors. So this part is all predicted. And then this is what's left. So this is a diagonal matrix in which each item gets its own residual variance and zeros everywhere else. What the zeros everywhere else mean, and this is another choice, is that there is no more relationship between any of these items. The only reason there was a relationship between any of these items is up here now. The residuals are unrelated. That is a choice. That is an assumption that is testable. If your analysis indicates that there is an extra relationship beyond what is implied by the factor, you can choose to make these off-diagonal zeros to be estimated instead. And they will plug the hole between what the actual relationship is and the one that's predicted. Okay, how are we doing? Mm-hmm.
So the idea is that you have all of the information on the sigma side, and then you, the model, estimates the other pieces, and you look to see how well each side matches.
Yep. Sigma is data. The rest of it is model.
Okay.
The rest of it is choices. And the choices is guided by what you think your items are measuring. How many things? So then here is, if you do the math to literally work out this matrix multiplication and addition, this is the result. And no, I'm never going to make you do this. I promise. So I have these boxed to show you within factor relationships. So here are the three items within factor 1, for instance. So here's my diagonal. The total variance for item 1 is here. The total variance for item 2 is here, and item 3 is here. And I just found a typo. Haha. We'll see if you can find it as we go through this. So how do we get to total? Well, total is true plus error. Total is the part that's due to the factor plus not the factor. So not the factor, that's my E variance right here. And you'll note that that shows up here. And here's E2. And this one, what should that one have been? That should be E3. My bad. So the factor part then is the variance of the factor that the item is measuring. So F1 is in all of these things. And it's the loading of that item on that factor squared out in front of it. Because when you take the expected value of something and you take the expected variance of it, any constants come out front and they get squared. It's just a math rule. So even if this first part of truth is off by a little bit, however much it's off is going to be plugged in by this error variance right here. So the diagonals are always going to be perfect to the extent that each item gets its own separately estimated error variance to plug the hole. And the same thing is true down here for factor 2 on its diagonal. Okay, with me so far? So off diagonals then, these are the predicted covariances. And they come from the variance of the factor and the loadings. So the covariance between item 1 and 2 is the loading for item 2 times the variance of the factor they share times the loading for item 1. Likewise, item 1 and 3, it's the loading of 3 times the variance of the factor they share times the loading of item 1. So you know what the answer is. You know sigma. You can ask for your covariance matrix to be spit out. This is what the model says it should be. It's not going to be perfectly right. How far off is it? That's what we want to know. And then last but not least, items that are from different factors, such as item 6 and item 3. They get a predicted covariance too. It's a function of each of their loadings onto their respective factors and the covariance between the factors. So the only reason that item 6 and item 3 have a relationship is because item 6 is measuring factor 2 and item 1 is measuring factor 1, and those factor 2 and factor 1 scores are related. It's that factor covariance that is responsible for the item covariance from items on different factors. It's the covariance between the factors that does it. So what this is saying in a nutshell is that the only reason that items 1, 2, and 3 are related is because they all measure factor 1. The only reason that items 4, 5, and 6 are related is because they all measure factor 2. And the only reason for cross-factor relationships is the factor covariance. And that's it. Yep.
So this makes me feel like if you have 15 items in a scale, there are many different possible ways that each item can be related to one or multiple factors and each other. So you can't test every single one with weights. Like, so for example, let's say I think the first factor goes back to 1 and the first factor goes back to 2. Oh, well, maybe the better model is one factor is items 1 through 6, and the other one's 4. And then, well, maybe 6 is actually 1 and 2. You know, there's like a million different combinations.
Yes.
So how do you do that?
So the fact that there are a million combinations and that you can set up your confirmatory model to confirm each and every one, some people would argue that the term confirmatory factor analysis is a misnomer because of that. But what's going to happen is that you have to start somewhere. You have to start with something. It may not be right, but you got to start somewhere. The information that you get back, one of the most useful diagnostics is that you will get this matrix back where each of these cells is going to be some sort of standardized number that tells you how far off you are. And so if you find out, say, that items 6 and 5, you had originally put them on 2 different factors, but they are really, really correlated, more correlated than your model says, you might want to rethink the fact that they're on 2 different factors. So it gives you guidance in terms of how the model doesn't fit that should dictate then what would logically come next. But you do have to start somewhere.
It suggests that this might actually be kind of a long and tedious process.
Yes.
Okay.
Very few times in my life at doing these analyses or in helping folks in this class do these analyses has their factor structure fit on the first try. Very, very few times. Yep.
Because everything's a little bit something else. Just identified, or is there any way right?
It's not just identified unless you've fully saturated the number of covariances with the number of factors that you have. So if you have 3 items, we'll get to this, but like if you have 3 items, there can only be 1 factor. If you have 4 items, there could be 1 or 2. If you had 5 items, so the math works out to where it's just identified if every single covariance is perfectly predicted by something in the model. The total number of possible parameters is equal to the number you spent. So let me go back to let's see, this picture right here. So we said in total, in the data, in sigma, there are 15 covariances between my 6 items, right? With me? Okay. I'm not spending 15 parameters to try and predict them. I'm spending 6. The factor loadings. The factor loadings are the reason for the item covariances. So I have 9 things left over that I could do. I could add more factors if this factor structure doesn't fit. I could add additional error relationships. But I've got 9 degrees of freedom, and that's literally the way you'll think about it, is degrees of freedom. So to the extent that 15 can be reproduced close enough with 6, you win. And you have empirical evidence for your factor structure. That's the idea. Okay. So yeah, the model is predicting covariance. That's what it's about. That's the whole story. All right. How are we doing? I know this stuff is a little dense. It gets easier as we go back over it. So we'll just keep reviewing as many times as we need to. So here's the thing about factors. They're imaginary. I need some way of nailing it down into numbers so that the rest of these numbers can be found. So there's 2 things that you also have to do when you're fitting these models besides determining which items go with which factors, and that is what's known as model identification. There are 2 distinct aspects of this. Number 1 is creating a scale for each latent factor. You have to have some way of putting numbers on it, or the whole thing can't work. Each factor needs a scale, and what that means, practically speaking, is that each factor needs to be given a mean and a variance. Here's the thing. It doesn't matter what they are. They just need something. And you can either borrow a scale from one of your items, or you can just arbitrarily say, my mean is 0, my variance is 1. Or my mean is 500, and my variance is 10. Doesn't matter. Once you've done that, then you have to make sure that your model is estimable and testable. And that's the harder part. And that is based on how many items you have, how many factors you have, and how many constraints you have. So we'll go over the first part of this, and then the second part. So here are 2 options for giving your pretend variable a scale with respect to its variance. Option number 1 is to just nail it down. I think my variance is 1. Okay, done. Option number 2. I think my variance is, I don't know. Instead, I'm going to borrow this number from one of my items. So in this approach, you end up fixing the loading for one of your items, doesn't matter which one, to 1. It's no longer estimated. It is nailed down instead. And then the factor variance becomes the reliable part of that item's original variance. So for example, if I had an item whose variance was 16, and I estimated a loading for it, translated that into a standardized loading of 0.9, I could use that same formula to figure out what the factor variance would be. It's the reliable part of item 1 times its original variance, works out to be 12.96. And that's what the model would do for you. It would slap 12.96 up here. Now you might be thinking to yourself, well, isn't 12 like a lot more than 1? Doesn't that cause problems? And it seems really arbitrary, but it is, but it's okay. So I have an analogy that I like to do for this, If you want to hear a quick story, not talk about matrices for a few minutes. All through high school and all through college, I waited tables to support myself. I think I've mentioned this before in classes. When I started at KU as a GRA, I actually made half as much money as I did waiting tables, which was a little depressing. But I learned the matrices in part because I never want to wait tables ever again. But I worked at a place called Grisanti's in Lincoln, Nebraska all through college, which is a lot like an Olive Garden, except they had loaves of bread that never ended instead of never-ending breadsticks. But they never ended. That was sort of the thing. And we sang for people's birthdays. We gave out a free scoop of spumoni, and our job as wait staff was to go corral everyone else. You had to walk around, can you sing? Can you sing? Can you sing? Can you sing? And try to get as many people who weren't actively running away from you when they saw the telltale ice cream in your hand. And you had to go over to a table, and the song went like this. Me, 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 me. Whoever got there first chose the key. And then we did, happy birthday to you, hey, happy birthday to you, ho, happy birthday, dear so-and-so. And then people of the opposite gender would lean in and say, baby, happy birthday to you. And then we clap and go back to our lives as waiters, wait staff. So in this experience, it behooved you to not actively run away if you were going to be forced to sing, because we all had birthdays and we all, you had to make sure you played fair. But whoever got there first and did the me, 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 got to pick the key. And if it was a girl who wasn't me, chances are it would be me, 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 me. And I'd be like, I can't do that. So I'd pick me, 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 in a nice, comfortable alto tone that I could handle for the whole song. This is just like that. It's still happy birthday, and people can still sing it even if you start down low or start up high. It's still happy birthday. The rest of the notes rearrange themselves so that the song still has the same distances between the notes. It's just like when you learn any kind of music, right? You can learn a song in C or D, and there's steps to translate from one key to the other. This is just like that. It really doesn't matter how you identify your model. Each of these is equally okay. The only catch, and why this one on the bottom is far more common, is because once you get into the SEM context, where each of these circles is going to be predicted by other stuff, once it's predicted and it's going to be an outcome, this factor variance has to have room to move to become factor variance left over. It has to be a findable number that's not nailed down into a constant. So in practice, what I tend to do is I do the first one, because this makes all of my coefficients readily interpretable, and I don't have to worry about how much a factor is. I know that if I have a factor score of 2, that's 2 standard deviations above the mean. It's 2, and so that makes it easy for me. Once I get into an SEM context where there's more than one factor, I have to switch to the bottom way. But either is equally correct. The only situation in which this bottom one is not correct, and I have actually seen this happen in someone's data before, if the item that you arbitrarily pick to be your marker, to have its loading fixed to 1, if that item is actually not related to the factor at all, then it has no reliable variance to pass up to the top, and your model can blow up. That's the only way that you can mess this up. Common things that I see people do that mess it up in practice just because of inexperience with the software. Sometimes I see people set their factor variance to 1 and set a loading to 1. Now think about why that wouldn't work. If your factor variance is 1 and your item loading is 1, what are you saying? Perfect. The item is perfectly measured by the factor. There is no error left over. Seems unrealistic. And your model may not fit very well if you accidentally identify it twice.
Would that be true if you used any number the same?
Yeah, you could make this 5. It doesn't matter. Then that's just like, happy birthday and F or whatever instead. Doesn't matter. So each factor needs a variance somehow. Easiest way to do it, call it 1. Each factor also needs a mean. Easiest thing to do, call it 0. So your factor is distributed as a z-score. Nice and handy. That is by far the most predominant way people do this. It is very rarely the case that you will see this other option used, but it is possible to borrow a marker item to set an intercept to 0 instead of the factor mean, and the factor mean gets estimated. The one situation in which you may do something like that is when you're doing longitudinal modeling of factors, in which case you want to see the factor mean change over time, and it needs to be estimated at later occasions in order to do that. So this summarizes then the 2x2 configuration of how your factor is to get a variance and a mean. What M+ does by default, and I think what most other programs do by default, is they estimate a factor variance. They force the first item's loading to be 1 unless you override it. It's a default. But they estimate all of the intercepts instead and fix the factor mean to 0. So long as this item that's the marker has any relationship with the factor, this should be okay. What I do over here is this one. The factor mean is 0, the factor variance is 1. It provides a convenient metric to look at all of the item estimates in. All right, how are we doing? Do you want to see what this looks like in M+, to tell it this information? Why not, right? We got a few minutes left. Let's do example 4. More real-world stories. So when I was a GRE, I think it was my second year of graduate school, I applied for a 25% GRE position to work with, it was the Heartland Forgiveness Scale project. It was Rick Schneider, who is now no longer with us, and his graduate student, Laura Thompson. I haven't looked recently, but this one paper from 2005 is by far and away my most cited paper, which is really funny because, like, I don't know anything about forgiveness. Laura was the first author, Rick Schneider was the second author, and I'm third. Well, Laura's no longer in academia. She's in clinical practice. Rick is dead, and I have a web page. So I get a lot of inquiries about whether or not people, they want to use the scale for their research and they want my permission. Anyone who's listening, go for it. It is publicly available. It's not my scale. There's a Heartland Forgiveness website you can go to that reads all the translations. It's been translated into like 20 different languages. It's a thing. It's a thing. And the common denominator is that they had done an EFA to get their scale structure, and they tried to publish a paper, and the reviewers were like, we want a CFA. And Laura's like, I don't know how to do that. And so then they paid me, and I learned how to do that. It turns out I didn't do it perfectly right on my first try. I'll tell you more about the story for the rest of the scale later, but for now I have 6 items that are supposed to measure forgiveness of situations. And in the battle for publishing this work, this was the most contentious scale. There were some reviewers who said flat out, I just don't believe that you can forgive a situation, so I'm going to reject your paper. But they wanted to invoke God or something else. The other subscales were forgiveness of self and others. I think of this as like the shit happens scale. Like if something happens and it's no one's fault, it just happens, like can you get over it? So, you know, when things go wrong for reasons that can't be controlled, uncontrollable circumstances, bad situations, negative situations that aren't anyone's fault, circumstances beyond anyone's control. So you can see the common theme here. The other thing that you can see is that they deliberately made sure that each of their subscales has 3 reverse-coded items and 3 not reverse-coded items. As it turns out, that is going to cause problems. So it is a 7-point scale in which 1 is almost always false, 7 is almost always true, and they did not provide numeric labels for 2 of the options. I did not get asked about that part. Here is the correlation matrix. So just as we stared at the heat map the other day to look at potential problems, I have colored some potential problems. What do you see here? Does this scale look like it's measuring one thing based on the patterns of correlation? Yeah, the correlations go all the way down from 0.2 up to 0.65. The items that are worded the same way are more related with each other than items that are worded differently. I don't have to know how to do CFA to stare at this and say, this isn't unidimensional. But they wanted it to be, so I will start with the unidimensional hypothesis. So here is the correlation matrix. Here is the covariance matrix that is actually going to be predicted. And here are the equations by which you can go back and forth. So all you need is the variance for each item and either covariance or correlation, and you can go back and forth to get the other one. The other thing is that at the top of the class, we talked about what kind of items these models are for. Normal and continuous, right? Here are the item distributions. What do you think? It's 7 points, though. It should be normal, right? Well, that's not what happened. Everybody's very forgiving. Or at least they wanted to say that they were. So welcome to M+. I have pasted in all of the relevant syntax and the selected parts of the output that you want to pay attention to. If you want to see what it looks like in its original format, you can download the handouts or the files that go with it. I also color-coded your handout so that it will match the color coding that you see within M+, where keywords are blue, comments are green, and everything else is black. So the same setup for all of the models to be presented is on this page right here. You can give your analysis a title if you want. You have to tell it where your data are. Now note the extension, DAT. That's a text file. M+ only takes text files. You have to take your data set from SAS or SPSS or STATA or what have you and convert it into either a tab-delimited, fixed format, or a CSV. I prefer CSV because you can double-click and they open in Excel, and that makes it easier to troubleshoot. But this one is a DAT file. Format-free means that it's individual data as opposed to a matrix. Here's the other fun part. You have to tell it the names of all of your variables. The variables are not in the first row. So it behooves you to cut your data set down to just what you need for these analyses so you don't have to type for years and years and years. Did you say you don't need to follow the same order as your data? Oh, yes, you do. Okay. Yep, it's the names in the order, and they have to be 8 characters or less. Because it's 1984 up in here, folks. M+ invested all of its resources in the models. The input and the output is straight up 1984. Welcome back to the future. So 8 characters, it doesn't know what they used to be called. So you can rename them whatever you want. So I wrote these out with R's behind them because it was going to help facilitate this lecture to sort of highlight which items go together for those reasons. You don't have to do that, though. You can also do dashes. So you can do something like this. Sit 1 dash sit 6, and it understands to expand that numerically. That's what I would recommend doing. I would never write out the items as separate names. Just give them a common stem and then keep track yourself if one's reverse coded or not. Missing data. In theory, it allows dots for missing data or blanks, but I have had very bad luck getting it to read data correctly that have dots or blanks, and so I'm superstitious and always fill in my missing values with a missing value code. ID variable. If you use this command, it will make sure that this column is attached to any of your output where you ask for factor scores so that you can merge them back into your data. Analysis, these are the options that we will use for CFA. Estimator equals MLR stands for maximum likelihood robust. We'll talk about that in a couple lectures. If you want to have factor scores saved as a data set, you can ask for it with this command. It will make lovely pictures for you if you do type equals plots. And then these are extra options that we will talk about later as well in terms of pieces of output to diagnose misfit and standardized solution. That's the one that we'll need. So to tell it what to do, it'll look like this. So comments are in green. They start with a exclamation point. So I have everything labeled here for you. To define a factor, you give it a name. It can be F1. I called mine SIT. It needs 8 characters or fewer. By is a keyword. It means measured by. After that, you list all of your items. The first item, by default, has its loading fixed to 1. Putting a star overrides that default to make it estimated. So star means go find the answer for this, versus an @ sign, which means tell it that it's going to be this number, fix it. So for instance, down here, sit at 1, that's telling it that its variance is to be fixed at 1. Don't try to find it, just call it 1. The rest of this are things that are estimated by default, and I'm writing them out so that you get used to how to refer to each model parameter. But if you don't like to type, this down here is literally all you need. All the rest of the loadings are estimated by default, and that's why you don't have to have stars. And then you do have to tell it what the variance is going to be. Everything else is already estimated by default. Each item gets its own intercept, its own residual variance, and the factor mean is 0 by default. So we have, I have lots and lots of examples in M+. I also want to point out a more general resource that I made on my book's website. Even though this book is not related to this class, it's my website for the book is called pilesofvariance.com. There is M+ code for that book, and in the front of that M+ heading, there's a general notes about program syntax handout that I made. And this is just all about the rules for M+ syntax, as well as examples of how you can make data files in SPSS, Stata, or SAS using proc export or export commands. And then all of the information about what each of these commands do is in here too. So we'll go over this, but this is also a resource that might be helpful to give more information. See, so that's not bad, right? No matrices. Just one sentence. Make sure you put the semicolon at the end. So we will get back to that then on Wednesday. Any questions before we wrap up? All right, thanks for your patience, and I will see you later. Thank you.